What if the birth of the universe was not a beginning but an escape? What if everything we see, the galaxies, the stars, the fragile cradle of Earth, was flung outward in a single breath from something older, stranger, and hidden? A universe does not arrive in silence. It erupts with impossible brilliance as if existence itself were torn open. The laws of physics, so steadfast in our daily world, bend and fracture in that moment. Time takes on a new shape. Space ripples like a living ocean. Some scientists have asked the unthinkable. Could the Big Bang have been a white hole, the opposite of a black hole? A place not of swallowing but of expelling. A doorway through which matter and energy were forced, spilling into the void. If so, our universe may not be the first. It may be the child of collapse, born from the ashes of another realm, carrying within it the memory of what came before. This vision changes everything. The Big Bang becomes not the origin of time, but a transition, a boundary between one reality and the next. The cosmos we call home might be an echo, the aftershock of a deeper truth. Why was it born? What lies behind the veil? And could traces of that ancient white hole still be imprinted in the very structure of space and time? The journey begins here, at the edge of mystery, where science reaches into the dark and asks what creation truly means. The story of white holes begins not with the stars but with equations. In 1915, Albert Einstein unveiled his general theory of relativity. It was a vision of gravity not as a force pulling at objects, but as the very fabric of space-time bending beneath the weight of mass and energy. Planets orbit the sun not because they are tugged, but because they follow the curved pathways of space itself. Within months of Einstein's revelation, a German physicist, Karl Schwarzschild, discovered something hidden in the mathematics. While serving on the Eastern Front of the First World War, surrounded by trenches and fire, Schwarzschild wrote down a solution to Einstein's field equations. His answer described what would later be called a singularity, a place where the curvature of space-time becomes infinite, a place where the known laws of physics collapse. At first, this was treated as little more than a mathematical curiosity. Even Einstein himself doubted whether nature could allow such an object to exist. Yet Schwarzschild's solution predicted something extraordinary. If enough mass were concentrated in a small region, space and time would fold so violently inward that nothing, not even light, could escape. The modern black hole was born, though no one yet gave it that name. But relativity's equations are symmetrical. They whisper of balance. If there exists a solution that swallows everything, there also exists a mirror solution that expels everything. Where a black hole represents an inescapable sink, a white hole is its impossible twin, a fountain. In one direction, matter collapses beyond return. In the other, matter bursts outward with no entry point, no past, only a beginning. The mathematics did not lie. White holes emerged naturally from the same equations that had given the world black holes. Yet to many they seemed like ghosts. Beautiful, perhaps, elegant in theory, but unmoored from any trace in the sky. It was in the 1960s that these phantoms began to take on substance. Physicists were no longer content to treat Einstein's equations as abstractions. They wanted to test them against the cosmos itself. Radio telescopes revealed strange and powerful sources of energy. Quasars, objects shining with a brilliance greater than entire galaxies, forced scientists to confront the reality of black holes. They were no longer exotic possibilities. They were anchors in the universe. In this new era, theorists returned to the other half of relativity's symmetry. If black holes exist, could their counterparts, white holes, also exist? Among those who ventured into this territory was Igor Novikov, a Russian physicist intrigued by the strange pathways that relativity permitted. Around the same time, the American physicist John Archibald Wheeler, famous for coining the term black hole, also gave shape to the idea of white holes. To them, the equations pointed toward a startling truth. A black hole and a white hole might be connected, joined through what would later be called a wormhole, a tunnel between two regions of space-time. In such a vision, matter falling into a black hole does not vanish. It travels. Somewhere, somewhen, it emerges from a white hole, an exit without an entrance, a beginning without a past. It was an idea that electrified imaginations, but it was also an idea that many dismissed. For one simple reason, the universe showed no evidence. White holes were strange in more ways than one. If they existed, they could not be entered. Nothing could cross their horizon from the outside. They would only expel, never receive. But how could such an object form in nature? What process could create something that spits out matter forever, without ever having absorbed it? Unlike black holes, which had observable fingerprints, X-ray emissions, stellar motions, jets of energy, white holes seemed absent from the sky. They were not just rare. They were invisible in principle. For decades, they were relegated to the margins of cosmology. Mathematical constructs, yes, but not physical realities. The balance of Einstein's equations was elegant, yet perhaps not reflected in nature. Still, the universe has a way of surprising us. By the middle of the 20th century, cosmology had entered a new age. The Big Bang theory, once controversial, was becoming the dominant explanation for the origin of the cosmos. Observations of the cosmic microwave background radiation, the faint afterglow of creation itself, seemed to confirm that the universe had once been in an unimaginably hot, dense state. Matter and energy had erupted outward in a great expansion. But one question haunted scientists. What triggered that expansion? Why did it happen at all? In the 1970s and 1980s, some theorists began to revisit the old ghost of the white hole. What if the Big Bang itself was not simply the beginning, but the explosive outpouring of a white hole? The equations of relativity allowed it. A black hole collapses inward, its matter seemingly vanishing into singularity. On the other side, in a new space-time, a white hole could burst into being. Our universe itself could be the other side of some cosmic bridge. This idea carried a profound symmetry. The death of one universe seeding the birth of another, a cosmic cycle where endings and beginnings are not separate, but two faces of the same event. Skeptics pointed out the difficulties. White holes, as described, would be violently unstable. Any slight disturbance from outside would collapse them. No evidence appeared in telescopes, no signals traced to their existence, and yet the question of the Big Bang remained. If the universe was once smaller than an atom, compressed into a singularity, then relativity demanded an answer to what lay on the other side of that wall. This is where the white hole refused to vanish. It lingered in the margins of theory, not as a visible object in the night sky, but as a possible explanation for the greatest mystery of all, the origin of everything. As physics advanced, the white hole found a new foothold. Quantum theory collided with relativity, showing that information might not be lost forever in black holes as once feared. If information is preserved, then perhaps the exit door, the white hole, cannot be dismissed. From Schwarzschild's solution in the muddy trenches of war, to the radio telescopes mapping quasars, to the cosmologists staring into the faint afterglow of the Big Bang, the thread remained. The equations tell us that white holes are possible. The sky tells us they are hidden. Between those two truths lies one of the deepest questions in science. Are we living inside the aftermath of a white hole? The story of their discovery is not one of telescopes catching their light, but of minds following the mathematics into the unknown. Each equation a step further into a reality, where creation itself may be the echo of collapse, and so, from the battlefield notes of Carl Schwarzschild to the visionary speculation of Wheeler and Novikov, the concept survived, not as proof but as possibility, waiting for a universe vast enough and strange enough to reveal whether beginnings can truly be born from endings. Here the discovery phase closes, but the mystery deepens. For if the Big Bang itself is a white hole, then every star, every atom, and every living being carries within it the memory of a collapse from another world. When the Big Bang theory took hold of 20th century cosmology, it brought with it both triumph and unease. Triumph, because the universe could finally be traced back to a singular event, a moment when all space, time, matter, and energy erupted into being. Unease, because the singularity at the heart of the Big Bang was not truly an explanation. It was a boundary, a wall of mathematics where known physics ended. Einstein's general relativity describes gravity with elegance, yet it collapses under the weight of infinity. The same equations that predict the gravitational collapse of a massive star into a black hole also describe the entire universe at the instant of its birth. Both are singularities. Both represent regions where density becomes infinite, and time itself ceases to behave as we know it. In this strange symmetry, black holes and the Big Bang become mirror reflections. One marks the end of time for everything that falls within its horizon. The other, the beginning of time for everything that has ever existed. If one solution exists in the equations, then its opposite must exist as well. A disturbing balance emerges. Black holes that swallow everything must be paired with white holes that expel everything. This idea was more than speculation. It was a mathematical demand, and it sent shockwaves through the scientific community, for it implied that the universe might not have sprung from nothing. Instead, it might be the outpouring of something older, a transformation rather than a true beginning. The shock came from philosophy as much as physics. For centuries, the idea of a cosmic origin had been wrapped in mystery, myth, and theology. To say the universe had a beginning was to suggest a moment of creation, unique and absolute. But if the Big Bang were in fact a white hole, then the notion of an absolute beginning dissolved. Time itself might be reversible under extreme conditions. Endings might become beginnings, and singularities might serve as gateways rather than dead ends. In the 1970s, a young Stephen Hawking began to explore the paradoxes at the heart of black holes. Together with Jacob Bekenstein, he showed that black holes are not entirely black. According to quantum mechanics, they should emit faint radiation at their boundaries, a glow now known as Hawking radiation. Over vast timescales, this radiation causes black holes to lose mass and eventually evaporate. This revelation was staggering. Black holes, once thought to be eternal prisons from which nothing escapes, could die. They were not only endpoints. They had lifespans. They had futures. And what is the death of a black hole? Does it vanish silently into the void, leaving behind only its faint radiation? Or could its evaporation be the trigger for something far greater? Some physicists suggested that the final death throes of a black hole might resemble a white hole in miniature. Matter and information trapped for eons could be expelled in a final burst. If that is true, then perhaps the entire universe began in the same way. The evaporation of a black hole in a higher dimensional realm, birthing our cosmos as a white hole explosion. The symmetry deepened the shock. A black hole at its end, a universe at its beginning, both bound by the same mathematics. The mirror seemed undeniable, yet this raised profound questions about the nature of time itself. Under ordinary circumstances, time is irreversible. A glass shatters but never reassembles. Stars burn fuel but never reignite their cores. Entropy, the great law of disorder, increases without end. But the singularities of relativity are not ordinary. They exist in conditions where space and time are warped beyond recognition. In those conditions, the arrow of time may bend. Some theorists propose that a black hole collapsing inward might appear on the other side as a white hole expanding outward. To one observer, time moves forward. To another, it is reversed. The implication was staggering. Time might not be a universal flow, but a local phenomenon, bound to the geometry of space-time. Where space-time bends infinitely, time itself could flip its direction. What we perceive as the birth of the cosmos might be, from another vantage, the end of something else. The idea was met with both fascination and resistance. For many, it challenged the cherished notion that the Big Bang marked the absolute beginning of time. If it was instead a continuation of something older, then the universe was not a singular miracle, but part of a larger, perhaps endless chain. Some cosmologists embraced this possibility. The cyclic models of the universe, in which each collapse seeds a new expansion, gained momentum. In these visions, black holes do not simply end. They recycle. Each singularity becomes the seedbed for a new cosmos, carried forward through the mechanism of white holes. Others were troubled by the lack of evidence. White holes remained hidden. No telescope revealed their presence. No signal traced back to their outpouring. The mathematics was beautiful, but beauty alone does not confirm reality. Still, the shock of the idea never faded. The symmetry between the death of stars and the birth of universes remained too precise to ignore. Einstein's equations, stubborn and elegant, refused to let go of the possibility. Hawking himself wrestled with the implications. If black holes evaporate, where does the information go? Quantum theory insists that information cannot be destroyed, yet relativity seemed to swallow it beyond recovery. The solution may lie in the white hole. Perhaps the information is not lost at all, but expelled. Perhaps what looks like destruction in one frame of time is creation in another. As these possibilities unfolded, the image of the universe shifted. No longer a singular beginning, but a balance of opposites. Collapse and eruption, death and birth. black holes and white holes, forever paired in the grand architecture of spacetime. The scientific shock was not merely in the equations, but in what they implied about humanity's place in reality. If time itself can be reversed, if beginnings and endings are interchangeable, then the story of the cosmos is far stranger than the human mind is prepared to accept. The Big Bang ceases to be an origin and becomes a transformation. Our existence is not the start of a story, but a chapter in an endless cycle of collapse and creation. The echo of this shock still reverberates today. Every discovery about black holes deepens the mystery. Every refinement of cosmology tightens the symmetry, and behind it all the white hole waits, not as a proven object, but as an inevitable consequence of the equations that describe our universe. In this balance lies the true disturbance. The notion that time itself, the most fundamental experience of human life, may not be absolute, that in the most extreme depths of the cosmos time can turn upon itself, birthing realities from the ashes of collapse. The scientific shock is not only the mathematics. It is the realization that the very boundary between life and death, between beginning and end, between past and future, may be an illusion. The cosmos, in its symmetry, demands that what falls must also rise. What ends must also begin. And in that symmetry, the Big Bang itself may stand revealed, not as the first moment, but as the most astonishing reversal of time ever conceived. At the heart of both black holes and the Big Bang lies a singularity, a point where equations strain under infinite density, where space and time themselves seem to fold into silence. For physicists, this parallel is more than coincidence. It is a mirror. The singularity that swallows and the singularity that creates share the same mathematical essence. They are different expressions of the same riddle. In Einstein's field equations, the singularity of a black hole emerges from collapse. A massive star burns through its fuel, gravity overwhelms pressure, and matter sinks into itself with unstoppable momentum. The curvature of spacetime grows without bound until it tears through the fabric of the equations. At that moment, relativity ceases to speak. The future ends. In the equations of cosmology, the singularity of the Big Bang appears at the other extreme. The entire universe is compressed into an unimaginably dense state. Every galaxy, every atom, every photon of light contained within a speck smaller than a proton. Again, the equations break. Time seems to begin not from a cause, but from a boundary. The past vanishes. Side by side, these two singularities suggest a deeper link. The end of one might be the beginning of another. The abyss of collapse could be the seed of expansion. In the 1930s, Einstein himself, together with Nathan Rosen, explored the possibility that black holes and white holes might be connected through space-time bridges. Their solution became known as the Einstein-Rosen bridge, what later generations would call a wormhole. In this geometry, a black hole does not simply terminate. It connects. Its tunnel leads to a white hole, a mirror mouth where matter and energy emerge. For an instant, the two are joined. One devours, the other expels. At first, these bridges seemed promising, but they came with complications. They would be unstable, collapsing before anything could cross. To stabilize them would require exotic forms of matter, with properties never observed. The mathematics was tantalizing, but nature appeared silent. Still, the concept endured, because it carried a symmetry that echoed the structure of reality itself. As physics advanced, the search for a bridge between collapse and creation found new frameworks. Among the most intriguing was loop quantum gravity, a theory that seeks to unite Einstein's relativity with quantum mechanics. In this vision, space and time are not smooth and continuous, but granular, woven from discrete loops at the smallest scale. In such a fabric, singularities do not truly exist. Instead of collapsing into infinity, a black hole might reach a minimum size and then rebound. This rebound, some theorists suggest, would be the birth of a white hole. The collapse of a star could ignite an expansion in another region of spacetime. On a grander scale, the collapse of a prior universe could spark the Big Bang of our own, a cosmic bounce where endings fold into beginnings, and the arrow of time reverses in the depths of geometry. Such ideas remain speculative, but they carry testable consequences. If our universe was born from a bounce, then the traces of that pre-Big Bang state might be written into the oldest light we can see, the cosmic microwave background. The CMB is a faint radiation that fills all of space, a relic from when the universe was only 380,000 years old. It is, in effect, the oldest photograph of reality. Its tiny fluctuations reveal how matter was distributed in the early cosmos, and from it, cosmologists extract the blueprint of galaxies and clusters that would later form. But hidden within that faint glow are anomalies, slight asymmetries, patches of cold and warm that do not fit neatly into the predictions of the standard Big Bang model. Some researchers have suggested that these anomalies may be the fingerprints of a deeper history. If our universe did not begin absolutely, but emerged from a bounce, then faint echoes of that prior contraction might still ripple through the CMB. In 2010, a team led by Roger Penrose proposed that concentric circles in the microwave background could be evidence of events that occurred before the Big Bang. Though debated, and far from conclusive, such claims ignite imagination. They hint that the boundary of creation may be porous, that the Big Bang is not an isolated spark, but a continuation of cycles extending into eternity. This possibility transforms the way science conceives of time. In the Standard Model, the arrow of time begins with the Big Bang carried forward by the expansion of entropy. But in a bouncing universe, time is not absolute. It flows through cycles. Contraction leads to expansion. Death leads to birth. The laws of physics, instead of breaking at a singularity, reconfigure themselves, allowing the story to continue. The shock of such a vision is profound. It would mean that the universe we inhabit is not unique. It is one among many, each born from the collapse of its predecessor. In this rhythm, white holes are not exotic outliers. They are the wombs of universes, and yet evidence remains elusive. The anomalies in the CMB may have other explanations. Quantum theories of gravity are still incomplete. Wormholes have not been observed. No white hole has revealed itself in the night sky. The bridge between theory and observation remains suspended in uncertainty. Still, the investigation deepens. Physicists continue to press against the boundary of the singularity, searching for the mathematics that can unite relativity and quantum mechanics. Each advance brings the possibility that collapse and creation are not separate, but phases of the same cosmic dance. To compare the singularity of a black hole with that of the Big Bang is to stare into a mirror that reflects not only physics, but philosophy. Both are boundaries of human knowledge, points where understanding falters. To say they are linked is to suggest that the universe is not a straight line of time, but a curve, looping through cycles of collapse and renewal. The possibility of a cosmic bounce does more than extend the timeline of the universe. It reshapes the meaning of existence. If our cosmos was born from the collapse of another, then creation is not unique. It is a rhythm, a pulse, a heartbeat echoing across eternity. For those who seek the origins of everything, this realization is both humbling and awe-inspiring. The Big Bang ceases to be a singular miracle. It becomes a chapter in a larger story, one written in the mathematics of symmetry, in the loops of quantum space, and in the faint afterglow of radiation that whispers of a past older than time itself. The deeper the investigation goes, the more the singularities of black holes and the Big Bang appear not as mysteries apart, but as twin expressions of the same truth. Collapse and creation, devouring and expelling end and beginning, woven together in the geometry of space-time. Here, the universe reveals itself not as a static structure, but as a living cycle. And the white hole, long dismissed as a phantom of mathematics, begins to emerge as the key to the most profound question of all: why there is something rather than nothing. The deeper physicists journey into the mystery of singularities, the more the universe seems to whisper of symmetry. A black hole collapses matter inward until it vanishes from view. Yet in the mathematics of relativity, that collapse has a mirror image, a reversal, where one devours the other expels, where one ends the other begins. This is the vision of a black to white hole transition, a cosmic rebirth where the death of one world ignites the creation of another. To imagine such a transition is to step beyond ordinary experience. In daily life, endings are final. Stars burn out, glass shatters. The arrow of time points only forward, never back. Yet near singularities, time itself bends. The collapse of a black hole might not be the silence of an ending, but the hidden seed of expansion. To an outside observer, the black hole appears eternal, swallowing light into endless night. But from within the depths of space-time, that collapse could rebound, emerging as a white hole explosion in another realm. If true, then black holes are not merely graves for stars. They are wombs for universes. This idea raises a question as disturbing as it is profound. Did the arrow of time itself begin in such a transition? In our cosmos, time flows in one direction because entropy increases. Disorder spreads, systems collapse into chaos. But if the universe was born from a white hole, then perhaps the very arrow of time was reset at that moment. What we call the beginning was not the origin of physics, but the resetting of time's flow. Before the bounce, entropy may have run in reverse. To us, that history is inaccessible, because our time began only after the white hole flared into existence. This problem of time is one of the deepest puzzles in physics. Time is not universal, as Einstein revealed. It bends, stretches, and slows under gravity. Yet in the deepest singularities it may even reverse. The Big Bang becomes not the start of time, but the moment when time's arrow was redefined. The white hole in this vision is not just the beginning of space and matter. It is the beginning of the very experience of past, present, and future. From this possibility, another question emerges. If black holes can transform into white holes, birthing new spacetimes, then could the black holes in our own universe be gateways to others? Every galaxy holds one at its center. Millions to billions of solar masses collapsed into invisible cores. Scattered across the cosmos are countless others, stellar remnants weighing 10, 20, or even 100 suns. If each of these black holes eventually transitions, then each might be a seed for a new universe. This vision reframes the night sky. Every point of collapse could be the hidden beginning of a new cosmos, disconnected from ours, expanding in its own space and its own time. The black hole we observe may be nothing more than the surface of an immense bridge. On the far side, a universe is born, forever out of reach. Some cosmologists, such as Lee Smolin, have gone further, proposing that this cosmic rebirth could drive an evolutionary process. In his cosmological natural selection hypothesis, universes that produce many black holes give rise to many offspring universes. Over cycles, the multiverse evolves, favoring the conditions that maximize black hole formation. In such a scenario, even the laws of physics may not be fixed. They may vary from universe to universe, shaped by which structures survive the process of rebirth. The implication is staggering. Our cosmos may not be unique. It may be one leaf on an infinite tree of universes, each budding from the collapse of its predecessor. White holes, then, are not just theoretical constructs. They are windows into the multiverse, portals through which creation flows endlessly forward. For some, this possibility is exhilarating. For others, terrifying. The human mind seeks singular origins, clean beginnings, and simple stories. To accept that our universe is only one of many is to abandon that comfort. The cosmos ceases to be a solitary miracle and becomes a cycle without end. The evidence for such ideas is not yet within reach. White holes have never been directly observed. Multiverses remain speculative, untested by experiment, yet the mathematics points toward them with unsettling clarity. Relativity demands symmetry. Quantum theory demands conservation. Between them lies the necessity that collapse and creation are linked, that black holes and white holes form a cycle. In this vision, our own Big Bang was not unique nor final. It was one transition among many, a flare of rebirth in an eternal chain. The universe is not a singular story, but a library, each book born from the ashes of the one before. This escalation of mystery deepens our understanding of what it means to exist. If white holes birth universes, then every atom, every star, every thought is the child of a collapse we cannot see. And if black holes in our universe birth new realms, then perhaps beings in those realms will one day look back upon their origins, wondering as we do what lies before the beginning. In the silence of space-time, the black to white hole transition is the most profound symmetry of all. It is the bridge between death and birth, between past and future, between the illusion of endings and the promise of infinite creation. And it leaves us with a question that cannot be ignored. If our cosmos is only one among many, born from the collapse of another, then what does it mean to search for ultimate origins? Can there ever be a true beginning? Or is creation itself an endless cycle forever mirrored across horizons we cannot cross? The mystery deepens, the night grows larger, and the white hole, still unseen, waits at the threshold of our understanding. The closer science approaches the edges of the universe's origin, the more the equations tremble. Relativity describes the collapse of stars into black holes and the expansion of the cosmos itself, but it cannot penetrate the singularity. Quantum theory explains the smallest scales with astonishing precision, yet it cannot tame gravity's infinite weight. Where the two domains collide, certainty dissolves. In this silence, theorists construct bridges of speculation, reaching for answers to the question of what came before the beginning. One of the boldest visions emerges from loop quantum cosmology. This approach grows out of loop quantum gravity, a theory that reimagines space-time not as a smooth fabric, but as a weave of tiny, discrete loops. In such a geometry, infinities cannot exist. Singularities vanish, replaced by a minimum volume that space-time can shrink to. In this framework, the Big Bang was not a true beginning, but a rebound. A big bounce. The universe, according to this vision, once contracted, collapsing inward until it reached that smallest possible scale. At that point, quantum gravity resisted further collapse. Space-time rebounded, erupting into expansion. What we call the Big Bang was the other side of a prior contraction. The beginning of time was not an origin, but a turning point in an eternal cycle. The cosmos has always existed, oscillating through phases of collapse and expansion, death and rebirth. The implications are profound. If loop quantum cosmology is correct, then the universe is not a fragile miracle suspended in nothingness. It is a rhythm, a pulse without beginning or end. Each cycle may erase much of the memory of the one before, but faint traces could remain. The anomalies in the cosmic microwave background may be those whispers, ripples of a universe that lived before ours. Another radical speculation arises from the holographic principle. Rooted in black hole physics, it suggests that the universe we perceive in 3 dimensions is a projection of information encoded on a distant boundary. Just as a hologram carries a full 3-dimensional image on a 2-dimensional surface, reality itself may be a projection from the horizon of space-time. If so, the Big Bang could be understood not as an explosion of matter from a singular point, but as the unfolding of information from a white hole boundary. The cosmos we see, galaxies, stars, and the very fabric of time, may be the interior projection of a surface we can never touch. In this framework, the white hole is not a violent eruption of matter, but the screen upon which reality is displayed. What lies before is the source of that information, inaccessible yet necessary. The Einstein-Rosen bridge offers yet another possibility. In this model, our universe itself may have emerged through a wormhole, a tunnel carved into space-time by the collapse of another region. If black holes connect to white holes, then the birth of our cosmos could be the outpouring of matter from the death of a parent universe. What we call the Big Bang may be the visible mouth of a deeper bridge. Such a possibility reframes the singularity not as an end, but as a passage. The equations describe a connection where time in one universe becomes space in another, where collapse in one domain becomes expansion in the next. To dwell on this idea is to confront a staggering image: universes giving birth to universes, threaded together through wormholes that forever remain hidden from direct observation. Among those who have pursued this speculation is Carlo Rovelli, whose work on quantum gravity has led to a hypothesis that black holes may not remain prisons forever. Instead, after vast spans of time, they may transform into white holes. The collapse does not end in silence. It rebounds, releasing information that had been trapped within. If this is true, then black holes in our cosmos are not permanent graves but delayed beginnings. Each one, after eons, could bloom into a white hole, expelling what it once consumed. This idea suggests that the universe is filled with seeds of creation, waiting to burst open after lifetimes longer than stars or galaxies. The white hole, once dismissed as a mathematical curiosity, may be the inevitable destiny of every black hole. In such a cosmos, rebirth is not exceptional. It is natural. Other speculative models explore even stranger territory. One such idea is false vacuum decay. According to quantum field theory, the vacuum of space is not truly empty. It is filled with energy fields that determine the laws of physics. Our universe may be in a false vacuum, a temporary state that only appears stable. If it decays into a true vacuum, the laws of physics themselves could change, rewriting reality. In this framework, the Big Bang could have been triggered by a tunneling event from one vacuum state to another. The white hole becomes not a geometric explosion, but a transition in the very fabric of physics. Another model envisions cosmic tunneling between universes. Quantum mechanics allows particles to pass through barriers they cannot classically overcome. If entire universes obey similar rules, then perhaps the cosmos can tunnel from one state to another, bypassing the impossible. The Big Bang, in this view, was a quantum leap, the sudden tunneling of reality from one configuration to the next. The white hole, in this sense, is the outward face of that quantum transition. Each of these theories seeks to describe what came before, and each carries a different vision of the universe's story. Loop quantum cosmology imagines a cycle, eternal and rhythmic. The holographic principle presents reality as a projection from a hidden boundary. The Einstein-Rosen bridge offers a cosmos threaded by wormholes, each birthing new realms. Ravelli's white hole hypothesis suggests black holes themselves may one day explode into rebirth. Vacuum decay and tunneling point toward deeper layers of physics, where universes may emerge as quantum fluctuations of existence itself. What unites them all is the refusal to accept the singularity as an end. Each theory replaces the silence of the singularity with a continuation, a doorway, or a transformation. In every vision, the Big Bang ceases to be the absolute beginning. It becomes a phase in a larger story, a transition from one state to another. The philosophical weight of these speculations cannot be ignored. If the universe is cyclic, then creation is infinite and beginnings are illusions. If the cosmos is a hologram, then what we see is only a shadow of a deeper reality. If we were born through a wormhole, then our existence is the child of collapse in another realm. If black holes transform into white holes, then the universe is filled with silent seeds of future creation. If vacuum states shift and tunnel, then the laws of physics themselves are not permanent but mutable. Each possibility reshapes the meaning of origin. None grants us the certainty of a singular beginning. All dissolve the comfort of absolute creation. Instead, they open horizons that stretch beyond imagination, where the universe is not a closed book, but an infinite library of cycles, projections, and transitions. For now, these ideas remain speculative. Observations are scarce. The cosmic microwave background offers faint hints but no decisive proof. Wormholes, if they exist, remain beyond reach. The transformation of black holes into white holes would unfold over timescales longer than the current age of the universe. Vacuum decay, if it occurs, could happen without warning, rewriting reality in an instant. These are not certainties, but possibilities. Yet speculation is not weakness. It is the necessary path when science meets silence. The singularity at the birth of time is such a silence, and into it, theory must reach. Each model is a lantern carried into the dark, illuminating what might lie beyond. And so, the investigation continues. Theories multiply, each drawing from the same equations, the same quantum fields, the same cosmic mysteries. None has yet claimed victory, but all point toward the same unsettling truth. The Big Bang was not the beginning. It was a threshold, a doorway through which the universe passed, from a state we cannot yet grasp into the reality we now inhabit. The deeper science presses, the more the white hole returns, no longer dismissed, but woven into the speculative fabric of origins. It becomes a metaphor for every theory that dares to say, before the beginning there was something. And from that something the cosmos was born. To peer into the origins of the universe is to wrestle with silence. The singularity at the beginning of time cannot be reached directly, for the laws of physics falter there. Yet humanity does not turn away. It builds instruments to extend its senses, machines that listen to the faintest whispers of the cosmos. Each tool is a lantern in the dark, carrying hope that the past may reveal its secrets. Among the greatest of these lanterns is the study of the cosmic microwave background. This radiation is the afterglow of creation, a sea of photons released when the universe was still in its infancy, only 380,000 years old. For billions of years, these ancient photons traveled unbroken, until they reached the detectors of satellites orbiting Earth. In the early 2000s, NASA's Wilkinson Microwave Anisotropy Probe, WMAP, mapped the tiny temperature fluctuations in this background. These fluctuations were imprints of density variations, the seeds of galaxies yet to form. Later, the European Space Agency's Planck satellite refined this map with exquisite precision, revealing a cosmos structured by invisible forces. From these faint patterns, scientists measured the age, composition, and geometry of the universe with remarkable accuracy. Yet hidden within these maps are anomalies. Slight asymmetries, cold spots, and alignments that refuse to conform perfectly to the standard model of cosmology. Some researchers suggest that these irregularities may hint at pre-Big Bang physics. If the universe emerged from a bounce or from a white hole-like eruption, its fingerprints may still echo in these patterns. The CMB in this way becomes not just a snapshot of infancy, but a possible window into what came before. Beyond the ancient light, another messenger carries news from the depths of space-time. Gravitational waves, ripples in the fabric of the cosmos itself. Predicted by Einstein a century ago, they remained hidden until 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, captured the tremor from the collision of two black holes. In that moment, humanity heard the universe for the first time, not in light but in vibrations of space-time itself. Since then, LIGO and its European counterpart, Virgo, have detected dozens of such events. Each signal is a story of immense violence, black holes merging, neutron stars colliding, the fabric of reality ringing like a vast cosmic bell. From these signals, physicists learn how matter behaves at extremes, where gravity and quantum theory collide. What might gravitational waves reveal about white holes? If a black hole were to transform, to rebound into a white hole, such a transition might produce a distinctive signature, a burst not of light but of space-time ripples unlike any other. Though no such event has yet been heard, the detectors grow ever more sensitive, poised for discoveries that could rewrite the story of beginnings. Another tool turns its gaze directly toward the shadows themselves. The Event Horizon Telescope is not one telescope, but many, spread across the Earth and linked together to form a planet-sized eye. In 2019, it captured the first image of a black hole silhouette, the glowing ring of matter circling the supermassive giant in the galaxy M87. For the first time, humanity saw the unseeable, a shadow carved into space-time by gravity so intense that light could not escape. By studying these horizons, scientists learn how black holes feed, how they twist space and time, and how jets of energy stream from their edges. Each insight into black holes is also a clue to their opposites. If black holes are real, then white holes remain possible. If horizons can be mapped, perhaps one day their mirror forms may be understood. The James Webb Space Telescope, launched in 2021, extends this quest even further. With its golden mirrors unfolded like a cosmic flower, Webb peers into the earliest galaxies, capturing light stretched across more than 13 billion years. In those faint glimmers, astronomers study how the first structures formed after the Big Bang. If anomalies exist in that early light, if galaxies appear too soon, or too ordered, they may point toward physics beyond the standard model, echoes of a pre-Big Bang state. Webb's observations, though focused on the dawn of stars and galaxies, may yet offer indirect clues about the conditions of the birth itself. Future missions aim even higher. Proposals for probes that would map the polarization of the cosmic microwave background with unprecedented accuracy. Gravitational wave observatories in space, such as LISA, designed to detect signals from sources unreachable on Earth. Each new tool brings the hope of catching evidence of rebirth, of transitions where collapse becomes creation. Even beneath the Earth, experiments seek the truth of the beginning. Particle accelerators such as the Large Hadron Collider in Geneva recreate on the smallest scales the energies of the early universe. In the collisions of protons, new particles flicker into being, revealing the structure of matter and the fields that govern it. These accelerators test theories of quantum gravity, searching for signs of dimensions beyond our own, or particles that could explain the dark matter shaping galaxies. If physics beyond the standard model is found, it may reveal the mechanisms by which singularities transform, by which black holes might one day rebound into white holes. Each instrument carries humanity closer to the threshold of understanding. Together they form a symphony of observation, from the faint glow of ancient light to the tremors of space-time, from the shadows of horizons to the sparks of particles. Each one pushes against the silence at the origin, probing the possibility that the Big Bang was not the beginning, but the transition of a greater story. The tools themselves embody a paradox. They are finite creations of a fragile species, yet they reach across billions of years and trillions of miles. With antennas stretched into the sky, with mirrors unfolded in orbit, with detectors buried underground, Humanity has built machines that stretch the senses to the edges of existence. And what do these tools reveal? Not certainty, but deepening mystery. The CMB maps raise questions as much as they answer. Gravitational waves sing of collisions but leave silence about origins. Black hole shadows confirm predictions yet whisper of greater symmetries. Webb reveals galaxies glowing in the first dawn, but the nature of time's first spark remains veiled. In each discovery, the white hole lingers, not as proof, but as possibility. A shadow in the mathematics, a hint in the anomalies, a silence in the data that begs for meaning. The investigation is ongoing. Satellites circle, detectors listen, telescopes unfold their golden eyes. Beneath the noise, the universe holds its secrets, and somewhere within those secrets lies the truth of whether our cosmos was born from nothing or from the rebirth of a deeper reality. The pursuit is relentless. The search is patient, and the silence at the origin remains the most powerful mystery science has ever faced. In the search for the beginning of the universe, humanity is not only exploring the cosmos, it is exploring itself. Every telescope pointed at the night sky is also a mirror. Every equation scrawled on a blackboard is also a question whispered inward. The quest for origins is a quest for meaning, for place, for purpose in a universe that stretches far beyond imagination. The possibility that the Big Bang was not the beginning but the continuation of something older reshapes this quest. It suggests that existence itself is an echo, that our galaxies, our stars, our fragile world all emerged not from nothing, but from the death of something else. The emotional weight of this idea is immense. It suggests that creation is not singular but cyclical, that what we call the birth of time may itself be a transformation, the re-emergence of reality from a deeper source. Paradox lies at the heart of this reflection. For centuries, cultures imagined the universe as a singular act, a first spark, a divine or natural beginning. The Big Bang seemed to confirm this intuition, presenting a moment where time and space erupted into being. But science, relentless in its logic, now whispers another possibility, that the bang was not the first explosion, but a continuation. That every beginning conceals an ending and every ending conceals a beginning. This realization humbles science itself. For all the power of equations and instruments, there remain questions that resist answers. What came before the universe? Why is there something rather than nothing? These are not only scientific puzzles, but philosophical abysses. To confront them is to recognize the limits of knowledge and the courage required to approach the unknowable. Einstein glimpsed this abyss when he wrote down the equations of general relativity. They revealed a universe dynamic and malleable, capable of expanding, collapsing, and curving under its own weight. Yet they also contained singularities, points where the mathematics broke and beyond which no prediction was possible. Einstein himself struggled with these implications, uneasy with infinities, reluctant to believe that nature would allow them. And yet, his equations carried them forward. Stephen Hawking stood at the edge of the same abyss when he proposed that black holes radiate and therefore die. For him, the singularity was not only a mathematical curiosity, but a gateway to paradox. If information could not be destroyed, then black holes could not be final. In their evaporation lay the possibility of renewal, the hint of rebirth. Though his wheelchair bound his body, his mind traveled to the farthest horizons, daring to ask what time itself becomes at its limits. Carlo Rovelli continues this journey, reimagining black holes not as tombs but as seeds. His work suggests that collapse may rebound, that black holes may become white holes after vast spans of time. To him, the universe is not a linear story, but a cycle woven from quantum threads where singularities do not destroy but transform. His vision asks us to accept not only the strangeness of the cosmos, but the possibility that rebirth is written into its fabric. Each of these thinkers approached the same mystery, each adding a fragment to the mosaic of understanding. None claimed to possess the final answer. Instead, they embodied the humility of science, the willingness to admit what is unknown while continuing to search. Their lives reflect the deeper truth, that science is not a fortress of certainty but a journey of wonder. And what does this wonder reveal? If the universe began as a white hole, then existence itself is a message, a release of matter, energy, and time from a deeper realm beyond comprehension. In this message lies no simple explanation but an invitation to question, to search, to imagine what lies before beginnings and beyond ends. For humanity to accept this possibility is to embrace both insignificance and significance. Insignificance because our world is one of countless outcomes in a vast and perhaps eternal cycle. Significance because the very ability to wonder about this cycle is extraordinary. Consciousness itself is part of the universe's echo, a reflection of the same forces that birthed stars and galaxies. To think about the origin of time is to be woven into it. The reflection grows larger when seen against the sweep of history. Thousands of years ago, humanity stood beneath the stars, inventing stories to explain their light, myths of creation, gods of fire and chaos, cycles of death and rebirth. Today, armed with satellites and equations, humanity tells new stories. Stories of white holes, multiverses, quantum bounces. Yet beneath the surface, the impulse is the same. To ask why. To search for the origin that explains the whole. Science does not end myth. It transforms it. The myth of today is the hypothesis of tomorrow. The speculation of today may be the evidence of the future. And in this cycle, humanity continues not with final answers, but with questions that deepen. Perhaps this is the true meaning of origins. Not to reach an ultimate beginning, but to recognize that there may be none. That existence is an unending river, with no first drop, no final ocean, but currents that flow forever. The Big Bang becomes one ripple among many, and we who live within it are part of the river's song. The story closes with reflection, but not with resolution. The white hole remains unseen, yet it persists in the mathematics, in the anomalies, in the questions that cannot be silenced. It is the echo of possibility, the shadow of a truth just beyond reach. If our universe began as a white hole, then existence itself is a message, an outpouring from a deeper realm beyond time. And we who question it are the echoes of a question that has no end.